So in this video, I want to talk about don't care condition for Boolean function simplification. Don't care condition. So in a real circuit, we not always need to have an output defined for every possible input. For example, some calculator display consists of a 7-segment LED. The LED can display 2 power 7 subtraction pattern, but we basically just use only 10 of them be used in our application. So if a circuit is designed so that a particular set of inputs can never happen, so we call this set of inputs as a don't care condition. Okay, they are very helpful to us in K-map circuit simplification, because if we know how to exploit the don't care condition, we may end up with a simpler circuit instead of using the real requirement of the output. So we may end up with a more complicated circuit. Okay, I'm gonna show what did that mean in an example later on. Okay, so basically we how do we exploit this one depend on the application, and also how can we combine with the existing value of 1 in the K-map in order to end up with maybe some simpler circuit. Okay, so here the an example in the K-map we have right here a don't care condition is identified by an X right here, and in the cell the mean term, and for example we have the for don't care condition right here corresponding to the values of 0 0 0 0 for W H Y Z. Okay, so don't care mean when the values of the input equal to 0 0 0 0, we don't care about the output right here. Okay, this can be either 0 or 1. That should be fine with the application we have. So in performing the simplification, we are free to include or ignore the values of H when creating our group. Okay, so we can consider this one as a 0 or 1. It depends on how do we group them together. Maybe we when you consider this one as 0, we can end up with a simpler circuit, or maybe when we consider this as 1, we can end up a more simpler with a simpler circuit. So we need to try and also to see which value is gonna end up with a better circuit. Okay, so let's see the example right here. So assuming the don't care condition as we had before. Now in this grouping, we consider this value right here is equal to 1, so we can group them together with the existing one right here we have. Okay, so if we consider this at 1, we can group for the values of 1 right here, and this can be represented by W naught and H naught. Okay, W naught, H naught right here for the first group right here, and the second group right here gonna be a all values of 1. Okay, so gonna be YZ. That's the first way we can consider the don't care condition right here. Okay, so in this grouping we assume that, or we consider the values of X right here equal to 1. Okay, so we can group with the existing one right here together. Another way we also can consider, instead of consider this one as 1, now I maybe consider this one as 1. Okay, so different way to group or to simplify the Boolean function by consider this as 1. So I can have the first group right here. The values of W gonna be 0, so gonna be W naught, and also the value of Z gonna be 1, so gonna be W naught Z. Okay, so for the pink group right here. So again, in this case, we consider this don't care condition X right here as a 1. Okay, Another group right here, that's O1, we're gonna have the same mean term right here. That's a YZ to represent this group. So basically, when you consider the don't care condition differently, we're gonna end up with a different simplified function right here. Okay, so in this case, we're gonna have the function represented by W naught Z or with the YZ. Okay, so that's the second function right here. So basically, if we consider the don't care condition differently, we're gonna end up with a different Boolean function right here. So the first one, if we consider in this case, we're gonna have the Boolean function of W naught, X naught, or with YZ. If we consider in this case where X right here equals to 1, we're gonna have a W naught Z or with YZ. Okay. Basically they are different. They are different Boolean function, and also they have a different truth table. And they have the different value as well. So it depends on the application and depend on the hardware circuit available to you. You may consider this one or consider this one. That's up to you. So as long as you have a better way to implement either this one or this one, so you can go ahead choosing this way to combine them together, or using this way combine them together. Okay, so so the key idea that you just depend on the application, depend on the resources you have, so you can consider the don't care condition differently, and to end up with the different circuits. That's gonna be a more benefit for your scenario. Okay. So that's a basic don't care condition, and if you know how to exploit don't care conditions, you can end up with a much simpler circuit compared with the existing one, or compared with the circuit if you implement only the variable 1 in this scenario, for example. So that's a basic information. So here's some conclusion for this lecture. So basically, in this lecture, we use the K-map for simplification of the Boolean function, and using K-map is provide an easy graphical method of simplifying a Boolean expression. And K-map is basically just a metric consisting of a output of the mean term of Boolean function, and we have introduced different rules and different ways to simplify 2, 3 excuse me, for input K-map, and this can be extended to any number of input through the use of multiple table. So here's the recapping the rule of K-map simplification. Grouping can only contain only 1 and no 0. Group can be formed only at the right angles. Diagonal group are not allowed. The number of 1 in the group must be power of 2. Okay, so it can be 1, 2, 4, 8, and so on. The group must be made as large as possible. So in case you can have multiple ways to group one together, so we need to select the largest one possible. Group can be overlapped and wrapped around the side of the K-map. So we have shown in different examples. You can see that the grouping can be wrapped around the edge, or from the top or the bottom, or from the edge of the K-map. And we can exploit the don't care condition in some scenario to simplify the circuit for the application. Okay, so that's a basic some information of the using K-map for simplification of the Boolean function. You can read more in the textbook.